This is video 1 for the Waves unit. This will be the final unit, and because of that there's going to be a lot of learning goals. Well, this is the final unit and the only unit in this grading period, so there's going to be a lot of learning goals for this one. Just one big idea. This is a big idea 6. We haven't seen this one yet. Waves can transfer energy and momentum from one location to another without the permanent transfer of mass. Also, waves serve as a mathematical model for the description of other phenomena. That gets into quantum mechanics and some other upper level, modern physics type ideas. So for this unit, like I said, we got a lot of learning goals. The first one, I want you to be able to use a visual representation to construct an explanation for the difference between transverse and longitudinal waves. I want you to use a graphical representation of a periodic wave to determine amplitude. I want you to be able to explain how energy and momentum are carried by sound waves. I want you to be able to use a graphical representation of a wave to determine period and frequency and describe how the frequency would modify the representation, or how changing the frequency would modify the representation. I want you to be able to use a wavefront diagram to demonstrate the observed frequency of a wave from some moving sources. I want you to be able to use representations of wave pulses to model the interaction of two colliding wave pulses. I want you to be able to predict the properties of a standing wave. And finally, I want you to be able to calculate wavelengths and frequencies of standing waves based on boundary conditions. It may seem like a lot, but really this might end up being one of the easier units. It's really not that bad. So first off, what exactly is a wave? So we're going to focus mainly on mechanical waves. There's two big classifications. We've got mechanical waves and electromagnetic waves. Electromagnetic waves are kind of reserved for AP Physics too, so we're just going to focus in on the mechanical waves. This is a disturbance in a medium. I want you to think about like a pebble falling into a pond. Once that pebble strikes the water, the disturbance is created, and that disturbance travels outward from the initial strike. We call that disturbance a wave. Now, if you think about it, the water bounces up and down, but it's not like the water where the pebble first entered it. It's not like those molecules of water travel to the other side of the lake. It's just the disturbance that travels, not the material itself. So, waves can propagate via different oscillation models, such as transverse and longitudinal. So the first type of disturbance is going to be a transverse wave. Here, the particle motion is perpendicular to wave motion. So I have a graph of a transverse wave, and notice we have to have some sort of particle oscillating up and down. So imagine a string where you take the end of the string and you shake it up and down. That will create waves that will travel away from where the shaking occurs. Now if you do just one shake, we call that a wave pulse, and that pulse will travel outward. If you continue to shake it up and down, then we have a periodic wave, which is just a collection of a bunch of wave pulses. So in your mind, try to think about the difference between a wave pulse and a periodic wave. Now, some examples of transverse waves. Well, a good example would be water. Another one would be waves on a string. A good example of that might be like a violin or a guitar or some sort of maybe like a piano, a stringed instrument where you strike a string that produces transverse waves. And also, even though we're not really talking about them a whole lot, but electromagnetic. We consider electromagnetic waves to be transverse. Okay, the next type is longitudinal. Now, longitudinal also has another name. It goes by it. We can also call this a compression. So you'll hear me go kind of back and forth between these two. I'll call it either a compression wave or longitudinal. I mean the same thing. So for these, the particle motion is parallel to the wave motion. So here we have something like a particle, and we're going to shake it back and forth in this direction, and that's going to cause the wave to travel parallel to the particle motion. We have a couple new different terms here. Where the material gets bunched up, we call that the compression, and again, that's why longitudinal is sometimes called a compression wave. Where the particles get stretched out, we call that the rarefaction. We can still have a wavelength, just like we did with transverse waves. The amplitude, you can think of the amplitude kind of like how thick the compression is or how stretched out the rarefaction is. And again, if I do this once, I can send a pulse. If I do this with some sort of rhythm, then I can have a periodic wave. So some examples. Very important example, sound. Sound is a longitudinal wave. Another type, certain types of earthquakes. We won't get into earthquakes too much, but there are certain types of earthquakes that we would consider longitudinal. So then, for propagation, mechanical waves need a medium. Electromagnetic waves do not. So when we kind of classify waves, we classify them into either mechanical or electromagnetic. Mechanical waves, which require a medium, we can have longitudinal and transverse, so like sound waves versus water waves. Electromagnetic, again, these are all kind of transverse. But those include light, so visible light, and then invisible light like microwaves, infrared, X-ray, ultraviolet, radio, gamma. So those are kind of like the big things, big topics for waves. So electromagnetics can travel through a vacuum where mechanical waves cannot. So if you find yourself trapped in outer space, no one can hear you scream. There's no medium for the wave to travel through. Okay. Now, many people think that for sound, the medium is air. And that's correct. Sound does have to have air to travel through. However, sound can also travel through liquids and solids, because the way we define sound is a mechanical wave or a longitudinal wave through some medium. So sound can travel through liquids and solids as well. Now for some parts of the wave, you guys probably have seen these before. Just a couple of notes here. Wavelength, I use the Greek letter lambda for wavelength. The amplitude is just from the rest position or the equilibrium position up to the top of the crest or down to the trough. So I can think about having positive and negative amplitudes. And we have, crests and troughs. Now, the time it takes to make one complete oscillation, so from the start point to right here, this would be one complete oscillation. The time it takes is what we call the period. So notice that this graph represents 3 oscillations, so 3 periods. And I use a capital T for period. We also have something called frequency. Frequency is 1 divided by the period. Period is how long it takes one oscillation to happen. Frequency is how many oscillations are there in 1 second. The way we measure frequency is with the hertz, which is an inverse second. So if something has a frequency of 1 hertz, that means we have 1 oscillation every second, and that means that the period equals 1 second. Since frequency is 1 over the period would equal 1 divided by the frequency. So if I had something with a wave with a frequency of 2 hertz, that means I would have 2 oscillations per second, and then the period would be 1/2 of a second. So just some more knowledge here. The amplitude then is the maximum displacement of a wave from its equilibrium value. And then classically, the energy carried by a wave depends upon and increases with amplitude. So for example, the energy that a wave carries is approximately proportional to the square of the amplitude. So in other words, if I need to double the amount of energy, I need to, or how about this? If I double the amplitude, I get 4 times the energy. So if I need to double the energy, I need to make the amplitude 1.414 times bigger, the square root of 2. Now, it should be noted that this is only for mechanical waves. Electromagnetic waves, the energy depends on frequency, not amplitude. So for a periodic wave, the period is the repeat time of the wave. So again, the period is how long it takes for 1 oscillation to happen. Frequency is the number of repetitions per unit time, so how many oscillations there are per second. So for a periodic wave, the wavelength is the distance, or the oscillation distance, so just like 1 complete wavelength. Now for some math for waves, the velocity, if we think about velocity, is displacement over time. What's nice is that for a wave, the displacement is going to be the wavelength, and waves always travel at a constant speed, or a constant velocity. So for a wave, its displacement is going to be its wavelength, and the time is going to be the period, because the period, the wavelength measures out 1 oscillation, and the period is the time for 1 oscillation. So we can use this formula to calculate the speed of a wave. But remember that frequency equals 1 divided by the period. So another way is to take the wavelength and multiply it by the frequency. And this is kind of the more accepted one, taking the wavelength and multiplying it by the frequency. And that's really all there is to it for the math. I mean, it's a very simple 3-variable equation. Notice if I take wavelength, which is measured in meters, multiplied by frequency, which is measured in hertz, which is an inverse second, I get meters per second. So everything works out. All right, that's going to conclude video 1 for the mechanical waves unit.